Okay, welcome to the review for the chapter on aldehydes and ketones, or carbonyl compounds. This is not chapter 16. This was chapter 13. This is not chapter 14, but chapter 13. Differentiate aldehydes and ketones. Aldehydes and ketones contain the carbonyl functional group. So it's a carbon, and pronounced carbonyl. Carbonyl. I don't know how to do phonetically, but it's carbonyl. That's how that's pronounced, carbonyl. And it is a carbon with a double bond to an oxygen, like that. Aldehydes have the functional group at the end of a chain of carbons, which, when you think about it, if it's at the end of a chain of carbons, carbon always has 4 bonds, so there's 2 bonds now to the oxygen. It's got room for 2 more, right? So this is going to be, on the left here will be to the left, this bond to the left will be to the rest of the chain, and that means it also has 1 bond to a hydrogen. So aldehydes have a hydrogen on this carbonyl. Ketones, they have the same functional group, but this carbonyl is in the middle of a chain. Okay, there's our carbonyl again, and on the left and the right we have more carbons. Now, the simplest ketone then has 3 carbons, right? And if you recall, aldehydes, these are derived from a primary alcohol, and they can be oxidized to an aldehyde. Ketones, these come from a secondary alcohol. So the oxidation of a secondary alcohol gives you a ketone. Naming simple aldehydes and ketones. Methanal, methane is our 1-carbon alkane, CH4, right? What we do is we drop the E ending and we add L, so methane becomes methanal, and this is also known as formaldehyde. So 1 carbon, that means there's 2 hydrogens. This is also known as formaldehyde. The common name is formaldehyde. This is actually a gas at room temperature. If you're used to formaldehyde being used for specimens in biology, that solution is actually called formalin, which is this gas formaldehyde dissolved in water. So formaldehyde is actually a gas. 2 carbons, ethane. We drop the E again, we add Al. So aldehydes end in Al. So there's ethanal. Okay. The common name for this would be acetaldehyde. We can talk more about where these common names come from later. They actually come from the acids which were used to derive these. So we'll talk about that more in the next chapter on acids. Acetone, also known as propanone. This is the simplest ketone that I mentioned before. Right. So again, we're going to drop the E of propane. Propane. We drop that E and we add -one. So ketones end in -one. Aldehydes end in Al, or if you wish in the common nomenclature, they'll actually end in aldehyde. I forgot benzaldehyde down here. Benzaldehyde, benzene, right? Here's benzene. Now, each carbon on benzene has a double bond and a single bond, so there is only 1 hydrogen attached to each one of these carbons like that. So you cannot have a carbonyl directly attached to the ring, so we have the carbonyl 1 carbon off like this. So that's That there's benzaldehyde. Should be methyl, should be an L there. Methyl ethyl ketone or 2-butanone. So when you get to more complicated ketones, there's a couple different ways we can name them. You can name the alkyl group. This is not working. The alkyl group that's in either end or on either side of the carbonyl. So we have an ethyl group, we have a methyl group. This should actually be ethyl methyl ketone. You might go to the hardware store and actually find it as MEK, which is methyl ethyl ketone, but these actually should be alphabetized. It should be ethyl, because E comes before M, ethyl methyl ketone. If you also notice, this molecule has 4 carbons in a row, which would make it a butane. But because we have a ketone here on carbon number 2, right, this would be 2-butanone. Let me draw another one here. 1, 2, 3, 7, something like that. Okay, so 7 carbons. Here we have the carbonyl on carbon number 3. So 7 is heptane, so this is heptanone. Drop the E, add one, 3-heptanone. For aldehydes, carbon number 1, if we had 1, 2, 3, 4, 5, the carbon containing the carbonyl is always carbon number 1. Okay, so you do not have to say, what is that, 1, 2, 3, 4, 5. You don't have to say 1-pentanal. This is simply pentanal. Drop the E, add Al, right? Because the carbonyl and the aldehyde is always at the end of a chain. It is always on carbon number 1. But with ketones, you do have to specify in the IUPAC system, using a number, where that one is, where that carbonyl is. Or you can name the 2 groups, the 2 alkyl groups that are on their side. So here we have an ethyl, and this is 1, 2, 3, 4. That's a butyl. Right? B comes before E, so this would be butyl ethyl ketone. Understanding the physical properties of carbonyl compounds. Aldehydes and ketones, this should be spelled correctly, and ketones, they will hydrogen bond with water, but not with themselves. I'll show you how that works. A hydrogen bond with water, but not with themselves. Okay, this means they are water soluble. At least the lower molecular weight ones, they're water soluble. And just as a rule of thumb, we'll say less than or equal to 5 carbons will be water soluble. Once they get bigger than that, they are not. But they still boiling points and melting points in alcohols that we talked about in chapter 12. Okay, so we'll take something, let's take acetone, very common. And it doesn't really matter if it's an aldehyde or a ketone. Here we have acetone, a ketone, or propanone. Right. The common name for this is acetone. I know it has 3 carbons. Acetaldehyde only had 2. I apologize for that. I'm not responsible for this naming. If you don't like that, then you can always name it using the IUPAC name here, propanone, right? So 1, 2, 3 carbons is propane. Drop the E, add one, propanone or acetone. There is no hydrogen attached to these oxygens. So there's no oxygen-hydrogen polar covalent bond as you see in aldehyde, in alcohols, or in water, right? And in water, I should write it. In water, we have these polar bonds. So we have partial positive and negative charges. In alcohols, we have this as well. So we see there's partial positive, partial negative, and that's what's required in order to set up hydrogen bonds. You don't have that in either aldehydes or ketones, so they do not hydrogen bond with themselves. But I could put a water molecule in here. Let me stick it up here. Right? Hydrogen's partially positive. This oxygen and the carbonyl is still partially negative, so we can still hydrogen bond to water, and that makes them soluble. All right, recognize the oxidation and reduction reactions for carbonyl compounds. We were introduced to this oxidation series back in the last chapter, and if you recall, start here with, let's make it 3 carbons, an alkane. Chapter 10. Chapter 11, oxidation is also it's the gain of oxygen or the loss of hydrogen. So I'm going to put minus H2 here. We lose a hydrogen, and we can form then a double bond. Right, so we lost 2 hydrogens. It was CH2, CH3. Now it's CH, CH2, so 2 hydrogens are gone. This is an alkene. Okay. We can add water across that double bond. This is not an oxidation, but just an addition reaction. And 1 hydrogen, we'll put the oxygen here. The OH, say, goes there, and the hydrogen there. Okay. Now this, of course, depends upon Markovnikov's rule, and I said we didn't really need to worry about that, so I'm going to redraw it in a slightly different way. I'm going to put the hydrogen that was added here and the oxygen here, and this is actually an anti-Markovnikov addition, if you care to know about such things. But the reason I want to start here is because if you recall, we can oxidize, this is a secondary alcohol. This guy is a secondary, and he can be oxidized to the ketone. So we get acetone, the ketone, and there it stops. If we try to oxidize this further, no reaction. Okay. However, this is a primary alcohol, and primary alcohols can be oxidized to the aldehyde. Right. Remember, aldehydes are at the end of a chain, and they have a hydrogen on the carbonyl, and then further oxidized to the acid. That will be the next chapter. So we're going to add another oxygen here. We get the OH. There's our acid group. Okay. So you should know this series. Alkane to alkene, add water across a double bond to get an alcohol. The secondary alcohols are oxidized to a ketone, and then they stop. Primary alcohols are oxidized to an aldehyde, and then highest oxidation state, the acid. Okay. Asking for specific uses of at least 2 carbon-carbonyl compounds. I didn't mention this, I think they mentioned this in the text, but I forgot to mention it in lecture. Benzaldehyde is actually has the odor of almonds. So it can be used as artificial flavoring. And there's another one, I think I did mention this one. This is called diacetyl, or 2,3-butanedione, also called diacetyl, or 2,3-butanedione. Right, so 2 ketones dione. And this is also flavoring. This is artificial butter flavoring. Acetone we had talked about. Acetone, and it's a good solvent. It's actually used as fingernail polish remover. And also MEK. I won't draw the structure of this one. MEK, these guys are used as solvents. And then lastly, we had formaldehyde, which is used, again, in biology class as, or actually also in the funeral home as tissue preservative. So not for food, right? But formaldehyde is actually toxic, but tissue preservative. Some other reactions besides just the oxidations, we have these addition reactions. Right? An addition reaction, remember, A plus B, they are added together, you get AB. So two reactions, one product. So an aldehyde and a ketone can combine to give you a hemiacetal, or a ketone and an alcohol likewise combine to give you a hemiacetal. Let's look at the structures for these guys. So a hemiacetal, we'll start with, what is that, propanal, and we'll have the alcohol methanol. Okay, and they combine, and notice now, why does it keep doing that? This carbon 3 here in the end was the carbonyl carbon. So maybe I'll put a little star here. Right? That was our carbonyl carbon. It gets an alcohol group. And then the alcohol, this methanol, this one carbon alcohol, gets bonded in an ether. So what you have here is this carbonyl carbon is now, right? This was a carbonyl carbon. Now it's a hemiacetal carbon. What is a hemiacetal? It's a carbon that has an ether linkage and an alcohol on the same compound. So not a carbonyl and an alcohol, that would be an acid. Right? Not a carbonyl and an alcohol, but an ether and an alcohol. And you can do the same thing with a ketone. So we'll start with, instead of propanol, we'll start with propanone. And we'll use maybe ethanol in this case. 2 carbon alcohol. So 1 CH3. Okay. So remember, this carbon in the middle, it gets the alcohol, gets the OH group, the hydroxy group, and then the alcohol is added through an ether linkage. So here we have the ether, and here we have the hydroxy attached to the same carbon. The only difference, I should maybe fill in hydrogens here. The only difference then between these two hemiacetals that I drew is the one that was derived from an aldehyde, right, has a hydrogen. Right? It's at the end of a chain, so there's a hydrogen here. Now if you take an aldehyde and 2 alcohol molecules, so this should be alcohol, right? You get not a hemiacetal but a full-fledged acetal, so acetal. Likewise, ketone and 2 alcohol molecules gives you an acetal. And the difference now is I'm not going to draw reactants. Just imagine we have 2 methanols here. Okay. This is just like what we had before. So there's 1 molecule of methanol that's added. The second molecule of methanol is added down here. So in essence, again, this is was our acetal, or sorry, this was our carbonyl carbon. Now it's our acetal carbon, and it's a carbon with 2 ethers. Carbon, oxygen, carbon. It's an ether linkage. Carbon, oxygen, carbon. So 2 ethers on the same carbon. You can do the same thing with a ketone and an alcohol. And again, I will just draw the product here. Okay, so we had our 3 carbon is our 3-carbon acetone or propanone. We're going to add 2 molecules of ethanol. So we have an ether on the top and an ether on the bottom. CH2, CH3, right? So 2-carbon alcohol, ethanol. Right. Again, carbon, oxygen, carbon, carbon, oxygen, carbon. So 2 acetals, or sorry, 2 ethers on the same carbon gives you an acetal. Right. A cyclic hemiacetal, or cyclic acetal or cyclic hemiacetal is, or sorry, intramolecular reaction. Molecular reaction. This is where one part of the molecule reacts with another part. I can show you that down below in a moment. A key feature of the cyclic hemiacetal is that it is stable. The other hemiacetals that I have up here, right, these hemiacetals are really, I'm sorry, not the acetals, but these hemiacetals are essentially unstable intermediates. Right. So a cyclic hemiacetal, the key here is if it's cyclic, it is stable. I'll say open chain or unstable. And we will see examples of cyclic hemiacetals when we start talking about carbohydrates. All right, so an example of a cyclic hemiacetal. Let's make this carbon number 1. This is carbon number 5. Carbon 1, carbon 5. So one part of the molecule reacts with the other part. Carbon 1, this is carbon 5. And we end up actually making a 6-membered ring now. Okay. This oxygen here, where this little purple line is going, becomes, this oxygen here becomes part of the ring. So here's our carbon, oxygen, carbon. That's an ether bond. But on this carbon here that had the carbonyl, this is carbon number 1. This is carbon number 5. This gets the alcohol, right? Just as it did up here, where the carbonyl carbon got the alcohol. So we have carbon, oxygen, carbon, ether here, and an oxygen here. That's a cyclic hemiacetal, and this is stable. It's not just a reaction intermediate, it's actually stable. But one other thing I should mention about these cyclic hemiacetals, I'd simply say these are found in carbohydrates. What chapter is that? Chapter 16, I believe. So, yeah, I believe it's chapter 16. All right. So this is a kind of a quick review of chapter 13 on aldehydes and ketones.